Okay, I'm going to write down the answers to the questions that we did at the end of class, just in case anyone wants to check their work, and use them as examples as they're doing the homework that's due on Wednesday. Otherwise, this video is really just a repeat. So if you got the questions correct, if I came by and said they were great, you probably don't need to check this video out. But if you want to check your work or you had a question about a step, you might want to watch these to see how to do these integrals. The first thing I'll note is apparently I don't know how to type the word substitutions. So we'll fix that. And then we changed the bounds on some of these. We did this one in class, and I think I put this was 0 to 1/2 for this guy, and then these were the other ones I think were correct. So I'm going to work through these. I may not show you all the steps because most of you did work these and did a great job in class, but in case you had questions about any of them, I did want to work the ones we didn't work in class, so you have all those for your notes if you want them. So this first one, hopefully you recognize it was really similar to this one that we did in class, but the thing that's a subtle difference is that there's already the +1. So on this one that we did in class, we had the 4 that we had to turn into a 1 because you want 1 minus something squared. And for this, hopefully you remind yourself that it does look a little bit like arctan, the derivative of arctan. So we would need something squared plus 1. So we already have the 1, so we don't have to worry about that. So the first step in this one is actually to get the something squared part. So it should be 2x is the thing that's squared plus 1. So that's something squared plus 1, and that's what looks like the derivative of arctan. So now we'll do a u substitution like we did over there. U is 2x. You get a derivative of 2, and then you're integrating u squared plus 1, and then a 1/2 du. Take care of the 2. And then you can change your bounds here. This is now 0 to 1. If you plug in your bounds, plug in 0 here, and then plug in 1/2 here. Then if we integrate this, this will give us 1/2 arctan of u from 0 to 1. And then the only other thing that some of you all had questions with or comments about was how to actually solve this. So this is 1/2 arctan of 1 minus arctan of 0, all in parentheses there. And then remember, this just means tan of theta equals 1 when theta equals what? So that's really what this is asking. That's what arctangent means. And if you remember unit circle, tangent is 1 at pi over 4. So this is just pi over 4, and if we ask ourselves a similar question for arctan of 0, that's at 0. So we get 1/2 times pi over 4, which is pi over 8, which a lot of you got, and that's really great. There's also a decimal answer. If you hadn't typed this into your calculator using your inverse tangent button, you probably got a decimal answer. But just be careful that your calculator is in radians mode, otherwise you will get incorrect answers. So just make sure you check that. Okay, we're going to work these two. These are a little bit easier. That first one is actually one of the harder ones. Here, this is hopefully you noticed, is a u substitution. And the big thing that I noticed is that this right here is the derivative of this. So if I let this be tan inverse, then I notice the derivative is 1 over 1 plus x squared dx. And so this just turns into the integral of 1 over u du, which is just natural log of u, don't forget your absolute value signs, plus c. In this case, that's ln of tan inverse of x plus c. So it's a pretty quick u substitution idea. The key thing to recognize is that the derivative of this appeared right here in the problem, and that's a symbol or a sign for you that this would be your u, and then this is the derivative of u, and that broke down really nicely. So it's a pretty straightforward u substitution that involves a tan inverse. This one is also a pretty straightforward substitution. Some of you did a u substitution, some of you didn't. I'll do it as a u substitution, but you actually don't even need to do the u substitution. You should be able to just see it for a lot of you. The derivative is a negative dx. So this is really just the standard integral that you would get here, which is 3 to the negative x. There'll be a negative sign to account for this negative in the u. And then remember, it's divided by the natural log of 3. I think some of you had times the natural log of 3. But remember, the antiderivative you divide by 3, natural log of 3, and the derivative you multiply by the natural log of 3. So this is just negative 3 to the negative 1 over ln of 3 minus negative 3 to the 0 over ln of 3. And if you simplify that, I think it's 2/3 ln of 3 on the bottom. And there's also a decimal answer for that you can check. If you type that into your calculator and your decimal answer is the same as that, that's also fine either way. So again, you could use this u substitution. There'll be a couple more steps if you did that. Otherwise, the antiderivative is really just exactly what the antiderivative would be with just an x there, but you have to account for that negative, so you put the negative out front. So a couple of options there, but again, a pretty straightforward u substitution problem, but with plugging in your bounds. If you had used the u substitution, this would have become a -1 and a 0, but it looks like I didn't actually end up using the u substitution. That's just if you did, that's what it would be. I just kind of went straight from here to here, which is also completely a legal thing to do. All right, one more problem here, and then I think there was also tangent of theta that was also left out. So this again is a pretty straightforward u substitution. We'll look at into our exponent there. X squared is something that we don't want to get rid of. We have no idea how to integrate that. So if we take that out of our exponent, we get this guy. And if we rewrite it, we have the integral. That's 3 raised to the u. And then it looks like a 1/2 from this situation here. Because we just want x dx. That's what's left over up here. So we want to take this 2 and divide it over. So that's the 1/2 du from that part. And now we're just integrating 1/2 the integral of 3 to the u du, and that's 1/2 times 3 to the u divided by ln of 3 plus c. And remember, the only thing you need to do there is replace that u with x squared. A little bit nicer way to write that might be 3 to the x squared over 2 ln of 3 plus c. That might be a little bit nicer. It's a little bit messy there. So that's your answer for that one. And then one more problem. The last one that was not in the notes, but I should put on the board as an extra one, was the integral of tangent of theta. And that's this cool little trick one that when you look at that, that's not an antiderivative that you know. So you have to rewrite it first. And this is a very standard u substitution problem because now you have a fraction, and if you let u be the denominator, so you can get rid of that nastiness in the denominator, the derivative of that is negative sine theta. And so when you rewrite this, you're really just integrating negative du over u, which is the same as negative 1 over u du, if you want to rewrite it. Which, remember, that integral is just natural log, absolute value, don't forget that, plus c. And then that really is just negative ln of cosine of theta plus c. If you look in your book, it'll often write it as the natural log of cosecant theta, which, if you know your log rules, you'll be able to see how you get from one to the other by taking the negative up into the exponent. But either of these answers, this answer is fine. But in your book, you'll often see this as the integral of tangent, and that's just using the log rules to convert it to cosecant.